Yes, sir.
So recording has started or?
No,
Yes, sir.
sir, it's
Started.
not started.
Now started.
Yes, sir, now started.
Fine. So let me share the PPT first. Can you see my slide on this radiation exchange? The last slide.
Yes, sir.
From
Yes, sir.
lecture. Okay, fine. So we concluded the last lecture on this slide, where we learned how to find out the heat flux due to radiation, Q double dot radiation, right? And I also asked you to note down how to calculate the emissive power capital E for a non-black body. You can calculate it using the expression E is equal to this epsilon sigma Ts raised to 4, right? Ts is the temperature of the surface. And what about the irradiation? So irradiation capital G is calculated using the formula sigma T surrounding raised to 4. Remember, this is different than this. Ts is surface temperature and T sir is the surrounding temperature. Fine. Now, based on this, we will solve the numerical where we'll try to find out the quantities like emissive power, the irradiation, and the heat flux due to conduction, heat flux due to convection, and then we'll try to compare the contribution of these two components. Fine. On this one. An insulated steam pipe passes through a room in which the air and walls are at 25 degrees centigrade temperature. The outside diameter of the pipe is 70 mm and its surface temperature and emissivity are 200 degrees centigrade and 0 0.8 respectively. So temperature is 200 degrees centigrade, emissivity is 0 0.8 epsilon. What are the surface emissive power and irradiation? So they have asked you to find out what is capital E, the surface emissive power, and the irradiation, capital G. If the coefficient associated with pre-convection heat transfer from the surface to the air is 15 watt per meter square, what is the rate of heat loss from the surface per meter length of pipe? So they have asked you to find out what is the convective heat transfer loss from the pipe to the surroundings, and as well as the emissivity they have mentioned. So you have to find out the heat transfer due to radiation as well. So heat flux due to radiation, right? So again we will talk about this 6 steps how to solve the problem. So the first thing is you will note down what is known to you. So from the data we know that we are dealing with the uninsulated pipe. Uninsulated means your pipe is allowing heat transfer to take place to the surroundings, correct? So uninsulated pipe of the prescribed diameter, what is the diameter? 70 mm. Emissivity is given 0.8 and the surface temperature is also given, which is 200 degrees centigrade. And this pipe is kept in a room with fixed wall and air temperatures. So the wall temperature is given. You can call it as a T wall or TS, whatever you want to name it. And the air temperature is also given. So T infinity or T air temperature, whatever notation you are using, let it be. In this problem, both temperatures are same, 25 degrees centigrade. So your T surface and your T infinity and T surrounding temperatures are one and the same, 25 degrees centigrade, right? Then the second point, you will note down what they have asked you to find out. So they have asked you to find the emissive power from the surface or surface emissive power, then the irradiation, capital G, and we know irradiation is what? It is the total incident radiation falling on the surface per unit area, right? And the last thing they have asked you to find out the rate of heat loss from the surface per unit length of the pipe. So for 1 meter length of the pipe, what will be Q? Or you can simply find out what is Q by L, the heat transfer rate per unit length, right? Then if you want, you can draw the schematic representation of the situation which is given, and then the assumptions. In assumptions, we know this is the steady state problem, right? Then the radiation exchange between the pipe and the room is between a small surface and a much larger enclosure. Now, why you are considering this second one assumption? See, you have a pipe, steam pipe like this, and this is kept in a large room like this, correct? larger. So don't you think this is something like a radiation exchange between a surface and a large enclosure or a surrounding? The second case from the previous slide, where there is net heat exchange taking place between these two surfaces, right? So we are considering this surrounding as a enclosure, larger enclosure. Clear? And then the analysis, how we will do the analysis. So we will use the formulas to find out what is Q convection and Q radiation, right? And at last we will comment on the contribution of the convective heat transfer rate and the radiative heat transfer. So maybe these two rates may be equal or may not be equal, or one will be dominating the other. Means, if the temperatures are sufficient or the temperatures are pretty high, then the radiation heat transfer may dominate the convective heat transfer. This may happen. So depending on the values of Q convection and Q radiation, you will comment on the solution. Clear? Is it clear? Hello?
Yes, sir.
Now I want you to solve this on your own. So you already noted down the formulas which we are supposed to use. Now this is the schematic representation. I am directly projecting it on the screen. You can use it as it is. So don't spend much time on drawing this. But look at how they have represented the data which is given. For example, they have written the surrounding air is there in the room. Temperature is 25 degree. Heat transfer coefficient. They have mentioned for natural convection. Then the diameter of the pipe is 70 mm. Capital L is the length of the pipe, and there is heat transfer taking place from pipe to the surrounding. So this Q dash is a, what is Q dash? So you can say Q dash is this Q by L, or the heat transfer per unit length of the, or per meter length of the tube. You can think like that. Then the surface temperature of the tube is 200 degrees centigrade, emissivity is 0.8, and then this symbol, this is important, emission which is coming out from the surface, so the emissive power of the surface, and this G which is the irradiation, the total incident radiation falling on the surface, and then the surrounding which is at same temperature 25 degrees centigrade. Before some time I explained this part, right? Now use the formulas which we have already talked about and find out what is emissive power E, then irradiation G, then Q convection, Q radiation, and then compare. Is there any other parameter they have asked you to find? Or this is the only thing you will calculate? Anything else? No, this is the thing you will calculate. Now find out. So tell me what is E now? Or tell me which formula you will use to find out the emissive power?
Epsilon rho Ts raised to 4.
So E is epsilon sigma Ts raised to 4, right? Now you should note down this. The temperature in the case of radiation should be taken in Kelvin all the time. We will follow this guideline. So use the absolute temperatures which are in Kelvin in case of radiation. In case of convection and conduction, we always talk about this delta T. So there it doesn't make any difference whether you use the temperature in degree C or Kelvin. But for radiation, you should use exclusively the temperatures in Kelvin. Remember this. Now what is the value of sigma? Stepan Boltzmann constant. You know this. Correct? Watt per meter square, K raised to 4. Now find out this emissive power E. So epsilon is the emissivity, which is 0.8, then 5.67 into 10 raised to power minus 8. And what is the surface temperature? So it's 200 plus 273, correct? Raised to 4. Tell me. What is the emissive power?
So 2270.48.
Just a minute. 2270.48.
48.
So what is the unit of emissive power? I talked about this last lecture. So the emissive power is 2270.48 watt per meter square. Now find out the irradiation G. How you calculate irradiation G? What is the formula? You must have noted down from the previous slide.
Sigma T surrounding raised to 4.
Sigma T surrounding raised to 4. So again 5.67 into 10 raised to power minus 8 into T surrounding temperature. This plus 273, right? (298), right? Raised to 4. What is G? Irradiation?
Four 47.14.
447.14. Unit will be the same, watt per meter square. So irradiation. Now find out what is Q convection. So I will find out Q convection. So we know this is given by HA Ts minus T infinity, right? Correct? Find out. And how you find out Q radiation? Heat transfer due to radiation. You have noted down from the previous slide, no? So this is flux.
Epsilon.
So Q will be A into sigma A epsilon Ts raised to 4 minus T surrounding with sigma A epsilon Ts raised to 4 minus. Correct? So find out these quantities. Now what is the area available for convection we will take here? Area. So this is a tube having outer
Pi d square by 4.
Is it pi d square by 4 or pi d L? See, the direction of heat transfer is normal to this surface, no? Getting me or not? See,
Yes,
heat
sir.
transfer is not in this direction. This is convection.
So sir, pi dl will be used.
So the area available for convection is pi dl, and not pi by 4 d square. Pi by 4 d square is this cross section area of the cylinder or this tube, right? Look at the direction. This is the radial heat convection. Convection is taking place in radial direction, right? So if you open this cylinder, what you see is this area which is available for the heat transfer to the surrounding. So remember, the area is pi dl and not pi by 4 d square. Now here you can take this L on this side and then you can say Q by L, or just put L is 1 meter and then also you can find out what is the connection. And Q. The answers are given on the screen. You can check. So this is total. This Q by L is the total of Q convection by L and plus Q radiation by L. Getting me or not? So this total heat transfer per unit length, or the rate of heat transfer per unit length, is sum of these two, convection and radiation. I have separately calculated these two, Q convection and Q radiation. So tell me these numbers first. and then you check whether sum of these two numbers is one and the same or not. 990. What is contribution of convection heat transfer?
577.27.
577.27. Okay. So this will be of course in the watt per meter, because I am taking this on the left hand side L. So you can say watt per meter. Or if you put L equal to 1 meter, then straight away you can write this as in watt also. Doesn't make difference. What about radiation transfer? Heat transfer? Do it fast. It's very simple.
Sir, 420.63.
420.63. So is it coming out 998 now, sum of these two, or not? Or close to this?
Yes, sir. आसपास आ रहा है.
ठीक है. So through this problem, what we understood is how to deal with the situations when you have more number of the heat transfer mechanisms or the modes of heat transfer, how to calculate their individual contribution, and then how to find out the total heat transfer from your surface, right? Now what is your comment about this comparison between convective heat transfer and radiative heat transfer? In this case, which one is contributing more?
Convection.
So convection heat transfer is slightly contributing more than the radiative heat transfer. So you may think about what will happen if you go on increasing this surface temperature. No? This surface temperature. So right now it is 200 degrees centigrade. So if you go to, let us say, 800 degrees centigrade or 900 degrees centigrade, you may find that the contribution of the radiative heat transfer may go on increasing. Right? Is it clear? So why I'm asking you to
Yes.
comment this is the reason behind, because we know that the radiative heat transfer, this is basically the function of the surface temperature of the body itself, of the surface, right? So this may change with the respective temperature. Fine. Now here is one more example. We are not going to calculate anything in this example. We will try to understand what are the different mechanisms by which heat transfer takes place in this typical problem. Fine. So the problem which we are going to talk about is the example of a thermos flask, which we use in our household, right? This. Or think it like your tea flask, where we store the tea at elevated temperature, right? Currently, right now, I have one thermos flask with me. So read the problem statement and then try to analyze this. So what we have right now is a closed container filled with hot coffee or a tea. This is in a room whose air and walls are at fixed temperature. Now see, two things are there mentioned, air and walls. So air is the fluid which is there in the room, and the walls. So you may think this as a surrounding T sir, or this as a fluid temperature T infinity, right? In that context, are at fixed temperature, and these temperatures are fixed. So we are talking about the steady state situation. Now identify. This word is important. What I want my students to do is they should be able to identify different modes of heat transfer. Now, if you go back and check our course outcome for this particular chapter, you will find that I want my students to identify different mechanisms of heat transfer in typical problem. So identify all heat transfer process involved in this that contribute to the cooling of the coffee. So we know that if the hot coffee is kept inside, the tendency is to get cooled, So the heat transfer will take place in this direction, doing this. Correct? You need not have to do engineering to comment on this. So comment on features that will contribute to a superior container design. So what I want you to think about is, based on your understanding of the different modes of heat transfer, you can think about the design, how the design of this flask should be made so that the heat transfer to the surrounding is minimized or can be minimized. Does it make sense? Have you understood what is this problem is all about? So you have the flask. It's a plastic flask inside this one, and then there is air gap, and after that there is a cover. And you are storing the hot coffee here, and this is kept in a still air or a room air. There is a large room like this, right? And air having the temperature. This is air, and this is your room wall, which is at fixed temperature. These temperatures are fixed. Under steady state, how the heat transfer will take place, we are talking. And what are different ways by which the heat transfer may take place. I think you must have already started thinking about where the conduction is possible, where the convection is possible, and where the radiation is possible. You must have started thinking in that direction. This is what I expect. Now, in next slide, what I am going to do is I am going to plot the exaggerated view of this cross section. So I am just going to talk about this part. So see what is involved here. So here coffee. Inside is coffee. Then there is a surface. So this is the plastic material. So it has got some thickness. So coffee to this surface, then to this material, that is plastic. Through the thickness of the plastic, then this surface, then the air gap which is present here, or the air space, then this surface, then this surface, then the thickness of the cover, then the inside surface of the cover, the outside surface of the cover, then the air which is surrounding the flask, and then the room wall. So this is how we should think about different possibilities of or the modes of different modes of heat transfer may occur in this case. Look at this. So first thing what I expect you to do is identify all the surfaces or materials involved in the heat transfer. So I actually helped you in the previous slide itself to identify the surfaces, different surfaces, and the materials also, like this plastic, then the cover, right? And second, identify all the possible modes of heat transfer. So we have conduction, convection, and radiation. These are the three modes. So we have to identify what all possible combinations may exist in this case. Note down all the fluids involved. Now what are the fluids involved here? Because as long as I talk about, or the moment I mention about fluid, it means I am talking about which mode of heat transfer? Convection. Convection, correct. So to find out the contribution of the convection or where the convection may take place, I should note down what are different types of fluids involved. So here we have coffee, then air. This is air space, and this air, the room air also. So air I am writing this twice. The same thing. I am assuming this air is different from this. Now look at how this problem is split into, or how the contribution of the conduction, convection, and radiation is thought about in this particular situation. So you just try to understand using these notations, and then I will project what is this Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, all these Qs. So currently just think about these terms, Q1, Q2. So what do you think, what could be Q1 now? So what could be the Q1? Now look at the arrow and tell me. So Q1
So heat transfer from the coffee to the plastic flask.
to the inner face of this flask,
Ah,
right?
yes.
Inner face of the plastic flask, right? So this is thickness of your flask thickness, right? So we know with this thickness there will be conduction taking place through this thickness, right? So this might be the conduction part, right? So this is convection, this is conduction. Then you will find the arrows like Q3. Now what is Q3? It is the convection heat transfer, and that too also maybe natural convection, because we are not forcing any fluid over the surface, right? So this can be a convection component from the outer surface to the air space, right? Now this can be a convection component, convection heat transfer from the air to the inner surface of the cover here, right? And what is this Q5? So Q5 can be thought of as the radiation heat transfer between these two surfaces, correct? Then Q6 can be thought of as the conduction through the thickness of the cover. This is conduction through the thickness of the cover. Then what about Q7? Q7 may be thought of as a convection from the outer surface
Convection.
to the room air, right?
Yes.
Convection. And Q8 can be thought of
Radiation.
as the radiation heat
Radiation.
transfer between your outer surface and the surrounding, the second case of the radiation, right? Is it clear?
Yes, sir.
So the problem which was looking like a very simple problem, now we understood that there can be the 8 components of this heat transfer, right? Different, and which involve all the 3 modes of heat transfer: conduction, convection, as well as the radiation, right? So I want you to note down all this. So Q1 is the free convection from the coffee to the flask. Then Q2 is the conduction through the flask. Q3 is free convection from the flask outer surface to the air. Q4 is free convection from the air to the inner surface of the cover. Q5 is the net radiation exchange between the outer surface of the flask and inner surface of the cover, right? Q6 is the conduction heat transfer through the thickness of the cover. Q7 is free convection from the cover to the room air. And last, Q8 is the net radiation exchange between the outer surface of the cover and the surroundings. Clear? So in this problem you have calculated nothing, but you have learned how to find out or how to note down the different modes of heat transfer in typical problem. Is it clear? Hello?
Yes, sir.
Yes.
Okay, fine. So remember, this has direct connection with the course outcome which I talked about in the first lecture. I want my students to identify different modes of heat transfer. Now moving further, that's all about introduction to heat transfer. Now we will actually jump into the next topic of discussion, that is the conduction. The first mode of heat transfer is conduction. So we will start our discussion with introduction to conduction. Now what is conduction? Just go through this slide. Most of the things on this slide we have already talked about. At least the Fourier's law of heat conduction we have talked about, right? So the conduction is a transport of energy in a medium due to temperature gradient. We already know this. As long as the temperature gradient is there, the conduction transfer will happen in the medium, right? And it requires a medium. We know this. Now, first point. Conduction is governed by the Fourier's law. So we know the governing principle or the governing law for the conduction mode of heat transfer is the Fourier's law of heat conduction. Fourier's law. Then second, use of the law, use of this Fourier's law to determine heat flux, will depend on the knowledge of the manner in which temperature varies within the medium. Means, how you will apply this law to find out the heat flux Q double dot will depend on how the temperature within your medium is changing. So for example, if you have a slab like this, and if your temperature is varying linearly, then you will decide how to use the Fourier's law to find out the heat flux Q double dot. So let us say in other case or other scenario, this temperature distribution is not linear. So it is something like this or like this, right? So it is not very linear. This is a different distribution compared to the linear. So under this situation, how to apply the Fourier's law to determine the heat flux will change. The approach will change. Correct? So it means to find out the heat flux Q double dot using the Fourier's law of heat conduction, you have to think about the temperature distribution first. How the temperature distribution is there within your material. Clear? Now the last point. The Fourier's law is applicable to transient. It is not just applicable for the steady state situations. It is applicable for the time dependent situation as well. So Fourier's law is applicable to transient, then multi-dimensional conduction. So don't what you can say restrict the application of Fourier's law to the simple case like one-dimensional heat conduction. So it is applicable for the multi-dimensional conduction and that too in complex geometries, right? So these bullets are important from your oral examination point of view. I may ask you a number of questions based on this in examination. So what is the actual use of Fourier's law? Is it applicable for this kind of situation or not? That type of questions I may ask in the examination. Fine. So these are the objectives for our this discussion on introduction to conduction. So what I want my students to understand when we finish the discussion on conduction. So only two bullets are there. The first is students should be able to develop a deeper understanding of the Fourier's law. They should understand how to apply the Fourier's law for a given situation. So I want my students to develop deeper understanding of the law itself. For example, what are its origins, whether this is something like first law of thermodynamics, second law of thermodynamics, or Newton's first law of motion, or is it different than these laws, right? So I want my students to understand what is the origin of this law. Then second, what form does it take for different geometries? So for example, if you have the simple cubical structure, you may talk about the Cartesian coordinate system. If it is a cylinder, you may think about the cylindrical coordinate system. If it is in a form of sphere, you may talk about the spherical coordinate system. So depending on the geometry, the form of the this law or the equations may change. So I want my students to understand that part also. Then the next one, how does its proportionality constant with thermal conductivity K depends on the nature of the physical medium. Means if I have a solid, how this K varies, I have a liquid or a gas, or is K depending on temperature. All that matter I want my students to have the deeper understanding about it. So how does the proportionality constant K, thermal conductivity, depends on the physical nature of the medium. Clear? Is it clear? First point, develop deeper understanding of the Fourier's law. You have to cross check at the end whether you are actually achieving these objectives or not through the curriculum.
Sir, can you please take back to previous slide?
Previous slide, I am going to upload all these slides, handouts. Don't worry.
Yes, sir, done, sir. Thank you, sir.
So the first point is over, deeper understanding of the Fourier's law. Now, in second point, what I want you to do is develop from the basic principles. Develop from the basic principles the general equation, which is termed as a heat equation, or rather I will call it as more specific about the conduction. I will say the heat conduction equation in Cartesian, cylindrical, and spherical coordinates. Okay. So we will derive, as I said before, we will derive the heat conduction equation in Cartesian coordinates in detail, and then I expect students to derive the remaining two equations, cylindrical system and the spherical system, on their own. based on the understanding of the Cartesian coordinate system. It's very simple. So the heat equation which governs the temperature distribution, this part is important. Temperature distribution. That's why it is marked in red. Temperature distribution in a medium in which conduction is the only mode of heat transfer. So we will only talk about the conduction mode of heat transfer hereafter, maybe for next 4-5 lectures. Then the solution to this equation, which will be a differential equation, maybe partial differential equation. The solution to this equation provides the knowledge of the temperature distribution. So we will use the different kinds of boundary conditions and try to solve the differential equation. And the sole aim is to get the temperature distribution out of this temperature distribution, which may then be used. Means I am going to use this information of temperature distribution along with the Fourier's law to find out the heat flux. So you understood what I am going to talk about in the coming 4-5 lectures. So my sole intention is to find out this component or this heat flux or the rate of heat transfer, something like this, right? Sole aim is to find out this, and for doing so I need the help of the Fourier's law of heat conduction, and only Fourier's law is not going to help me. What I need extra is the temperature distribution, right? And to get the temperature distribution, what I need is the differential equation of heat transfer. And to solve the differential heat equation, I need different kinds of boundary conditions, right? So this is in reverse I explained. So our intention is to find out the heat flux. For that we need the help of Fourier's law, and only Fourier's law is not going to help me to find out heat transfer rate or the heat flux. I need the temperature distribution along with the Fourier's law, and to get the temperature distribution I have to solve the differential equation of heat conduction, and to solve the differential equation of heat conduction what I need is different kinds of boundary conditions. Is it clear?
Sir. Sir.
Go ahead.
Sir, thermal resistance हमने मतलब नहीं सीखा ना.
No. We have not yet introduced what is thermal resistance or thermal contact resistance. We have not introduced. Still,
Okay,
we have a
sir.
long way to go before we introduce that. Eh? Hello. Now, can I go to the next slide?
Yes, sir.
Okay. Now look at this experiment. The name of the experiment is the steady state conduction experiment. Look at the diagram. So what do you see on the top left corner? Is something like a rod, cylindrical rod.
Pipe, sir.
Consider this is a solid rod, not pipe. If you say pipe, then it will be it's hollow, no? So I don't want it to be considered as a hollow pipe. No? Consider it as a solid bar in that case. Okay? Hello?
Yes,
Is
sir.
it clear? Consider it as a solid
Yes.
bar of this length delta x, right? And the diameter, whatever you want, you take diameter. Capital A is the area, cross-section area of this rod. T1 is the temperature of the left face, T2 is the temperature of the right face, and from diagram it is clear that the left face is hotter compared to the right face. So temperature T1 is greater than T2. So the direction of heat transfer is from left to right. Now why I have shown this direction of heat transfer like this? Because this peripheral thing is insulated. This is insulation. So all over the periphery, the insulation is applied. This is insulation. So there is no chance for the heat transfer to take place in this direction. This is a restrictor. So we have only the one-dimensional heat conduction in x direction. Is it clear? Hello. Is
Sir,
it
can you
clear?
repeat once
Yes,
more?
sir.
See, there is no heat transfer taking place in radial direction for this bar. The heat transfer is taking place in only one direction, that is x direction, one-dimensional heat conduction. Clear? Because this is
Yes.
insulated, periphery is insulated. So there is only one way by which heat transfer may take place, that is from left to right. And why from left to right? Because this end is hotter than this, which is mentioned here. T1 is greater than T2. And what is delta T? Delta T is called as the overall temperature difference, which is this temperature T2 and difference between this temperature T2 and T1. So as I have mentioned delta T, I am writing higher temperature minus lower temperature. But you may write sometimes when you write dt by dx, you will write it like T2 minus T1 by L, right? We have learned about this in the previous lecture, right? So you will write final minus initial, correct? So here we are talking about only the overall temperature difference, delta T magnitude. That's why I have written T1 minus. So don't get confused with this. Is it clear? Now note down these notations. So what is delta T? Delta T is the overall temperature difference, which is given here, delta T. Now what is delta X? Delta X is the length of this rod, delta X. And capital A is the cross-section area of the rod, which is shown here, right? And based on our understanding of the Fourier's law, which we have already talked about in the last lecture, we know that the heat transfer by conduction, this is the rate of heat transfer and not the flux. So the rate of heat flux, the rate of heat transfer is proportional to the temperature gradient along that direction, x direction, and is also proportional to the area normal to the heat transfer or rate of heat transfer, right? We talked about this. So same thing I am just writing here. So Qx is proportional to the area normal to the heat transfer. So this is the direction of heat transfer. This is the normal area, right? A. And then this dt by dx is written as the overall temperature difference delta x, and this is the length of your rod delta x. Clear? So note down this expression and then come to these two bullets. Now this is true. This is true for any material. So initially I am considering this as a metal rod, let us say, metal rod, a steel bar or a brass kind of material you can think of. So Qx is proportional to A and is also proportional to delta T by delta X. This is what my observation is through the experiment. So the rate of heat transfer will depend on these three parameters: A, delta T, delta X. These are the three variables which I already noted down. Right. So in changing the material from metal to plastic, this proportionality remains valid. So what we will observe through the experiment is, even if you replace this metal bar by something like a plastic bar, let us say, then also Qx will be proportional to A and Qx will also be proportional to delta T by delta X. Clear? So the proportionality will remain intact even if you change the material of this rod or bar. Is it clear? Then, so this we will observe through the experiment itself. Then the second point, for equal values of A, delta X and delta T, the value of Qx would be smaller for the plastic than for the metal. Now what you have to do is, you have to keep all these parameters same for metal rod as well as plastic rod. This is what the second bullet is talking about. So if you keep these dimensions same for both rods, again through the experiment you will observe that the value of Qx is smaller for plastic compared to the metal rod. Clear? Now note down this expression. Qx is K delta T by delta X. Now again I am writing this in absolute term, that's why minus sign is not written here. Qx is K delta T by delta X. So this delta T I am directly writing T1 minus T2. That's why this minus sign is not written here. I already talked about this. Correct? So when you are writing it in terms of delta, that's fine. But when you are writing it in terms of the differential, then minus sign is there. See here. Right? So if you evaluate this expression with the limits delta x tends to 0, then the same expression can be written in the form of a differential term like dt by dx. So under the limits when delta x tends to 0, what is the limit? Delta x tends to 0 means this length of the rod will tend to 0. What will happen to this? Then this delta will be replaced by d, differential, or a very small the differential component. You know this from mathematical background. So straight away I can write now that the Qx the rate of heat transfer along x direction must be equal to minus Ka dt by dx. Now why I jumped from this to this expression is given in this. Under the limit I have to solve this. So I will get Qx as minus Ka dt by dx, and then the heat flux Qx double dot, which is nothing but the rate of heat transfer per unit area, so Qx by A. So this will be minus K dt by dx. So that A here is taken on the left hand side, and then I am writing it as the heat Qx double dot. So is it clear how we derived this? Qx double dot is minus K dt by dx.
Yes, sir, clear.
So remember, this is for conduction. No? The conduction heat flux Qx double dot is given as minus K dt by dx. Now can I go to next slide?
Yes, sir.
Yes, sir.
Now continuing our discussion from the previous slide, what I want you to note down is, remember heat flux is a vector quantity and it is not a scalar because it has got the direction. Wherever I talk about this term Q double dot, it has got always the direction like this or this. So it is a vector quantity. So note down this. I may ask this in oral examination. So heat flux is a vector quantity, right? So this can be written in vector form now. So Q double dot heat flux can be written as minus K del T. Now what is this del? You know this. What is del, operator? So it is dou by dou x plus dou by dou y plus dou by dou z, right? Del operator. We must have studied it in mathematics. So I am just expanding this del here, and I can write that the heat flux Q double dot is given as a double dash is equal to minus K into bracket I dou t by dou x plus j dou t by dou y plus k dou t by dou z. Right? So the temperature gradient along that direction multiplied by along the direction multiplied by the unit vector along that direction. So dou t by dou s is the temperature gradient along x direction. Multiply this by the unit vector along x direction, which is I. So same way for similarly for y and z direction, right? So note down this expression: u double dash is equal to minus k into bracket I dou t by dou x plus j dou t by dou y plus k dou t by dou z. Noted?
Yes.
Yes, sir.
Now look at the diagram at the bottom left corner of this slide. What we see is the temperature plot, right? Temperature distribution. So temperature is function of the x alone. So it is plotted on y-axis, and on the x-axis we have the length of that rod, right? Length of the rod. So don't think that this is the temperature distribution for a slab, huh? Getting or not? So the temperature is varying, or the heat transfer is taking place in x direction alone, right? For that rod. So the temperature distribution will be like this only in case of that rod. So on the left face, temperature is T1. On the right face, temperature is T2. And I'm considering the linear temperature distribution. And the direction of the heat flux will be from left to right, like this, Qx double. Clear?
Yes,
Hello.
sir.
Now
Yes, sir.
suppose in the same rod like this, if I consider the heat transfer along this direction, the heat flux along this direction, radial direction. So what I am talking about is this is radial surface of the cylinder, right? This is true when this side is insulated and the heat is conducted in this direction. So that time I am saying the temperature distribution is like this, correct? So what I want you to understand is the direction of the heat transfer or the heat flux is normal to this face, right? Or the surface. Do you get my point or not? I repeat, the direction of the heat flux is normal to the surface. Clear? Now how you will resolve this if you have this kind of surface, curved surface? So this curved surface represents constant temperature. That's why I am calling this as an isotherm. Isotherm means a surface or you can say isothermal surface, means the surface which has got constant temperature. So this may be the temperature, let us say T, and now you want to find out what is the heat flux through this surface. Then what you know is the direction of the normal vector is perpendicular to this surface. So at this point it is perpendicular, but if I change the point, then the direction will change, no? Because I have to take the normal direction. So if I change the point, the direction will change. So this will keep on changing for the curved surface like this, right? Are you getting my point or not? Hello.
Yes, sir. Yes, sir.
So in
Yes.
this case, how I am going to write what is the heat flux normal? So I may denote it as Q double dash N. So this N indicates the heat transfer in normal direction or normal to the surface. So I can resolve this into, let us say, the two dimensions for this kind of situation, 2D plane. So I can say Qx double dot and Qy double dot. So this will be calculated based on these two. Is it clear?
Yes,
For
sir.
random geometry.
Sir,
Huh.
sir, in the previous diagram, sir, the heat flux is normal to area, sir. So the area will be pi r square, na? I mean pi d square by 4.
So in that case, it will be pi by 4 d square. See
Okay,
here,
okay, sir.
the area normal to the direction of heat flow is this face area, this one, correct? So conduction is taking place in this direction, right? Are you getting my point or not? And before this, there was convection taking place through this surface, the peripheral surface. No? That's why we took area as pi dl, and it is not pi dl here. It is pi by 4 d square for this case. I hope you understood this.
Yes, sir. Yes,
Okay.
understood.
Now note down how to write down the radiation, the conduction heat flux expression. So Q double dot. If you know the heat flux along x, y, and z direction, then you can find out the total heat flux Q double dot I Qx double dot plus J Q double dot Y plus K Q double dot Z. So take into account the heat flux along all the three coordinate directions x, y, and z, and from that find out the total heat flux Q double dot. Clear? Is it clear?
Yes, sir.
Now write
Yes.
down the expression for these individual components like this. So Q double dot x is the heat flux, conduction heat flux along x direction, which will be given as minus K dot T by dou x. Q double dot y is the conduction heat flux along y direction, which is minus K dot T by dou y. Similarly for z direction. Note down these quickly. Don't spend much time on this. Otherwise, it will be very difficult for me to finish your syllabus in 36 hours. Note it down. Keep habit of writing all those expressions. Don't wait for me to upload all these slides. In examination, you will not be in position to write it if you do not have the habit of writing the equations. You may be knowing part of this, but you will not be in position to reproduce it in the examination. So keep habit of writing the equations. So what we conclude from this conduction experiment is, number one, the heat flux is a directional quantity, means it is a vector quantity, it has got the direction. Then the second thing we conclude is the direction of the heat flux Qx, Q double dot x is normal to the cross section area A, is normal to the cross section area A. So for the plane surface, it was like this, the plane surface, we learned that it is like this, and for the curved surface, it is again normal. So irrespective of the nature of the surface, the direction of the heat flux is always normal to the surface, right? The second point. Now the last point, the direction of heat flow will always be normal to the surface of constant temperature. Now remember, when I'm saying that this direction is normal to the surface, for this entire surface, I am saying that the temperature is T1. So this is isothermal surface. Same is true here also. When I am saying the direction of the heat flux is normal to this, it is hidden here that the temperature of this entire surface is one and the same, which is T. Isothermal surface. I hope you understood. Correct?
Yes.
Hello. So I think it is time to stop now. We are close. Just wait for a minute. Let me download the attendance first. Now, those who are regularly attending the lectures,